Hi, everyone. Getting pretty close to the end here. I sent out the final. I sent out a notification about that. Hopefully you've had a chance to take a look at that. Please, if any questions arise on that, let me know. I'm definitely willing to answer clarifying questions. That is definitely something I'm more than happy to do for you. Again, if you run into some serious issues on it where you're just not even sure what's going on, please reach out. Let me know. Okay. So we have 1.5 lectures to go. This will probably be kind of a short lecture, and I'll split, just so I'm not rushing, I'll probably split this between this lecture and the one for Monday. But hopefully the first lecture on hypothesis testing made sense. One of my goals here is to kind of expose you for the first time to a hypothesis test and also show you the connection between a hypothesis test and confidence intervals that we were doing before. Okay? So just to remind you, these were the steps in the hypothesis test. You want to identify the parameter of interest that you want to know something about, like the mean or the variance. You state the null hypothesis. Remember, that always has equals present. You state the alternative hypothesis, which isn't exactly the opposite, but it's always either not equals or greater than or less than in relationship to the parameter of interest. Like, the mean is greater than 95 or the mean is less than 95, depending on the situation at hand. Okay. You write the formula for the test statistic. A lot of times that will be like converting the thing to like a z-score or something, subtracting the mean, dividing by the standard deviation. Okay. In the case where you have fair confidence that the central limit theorem is fully in play, you will then use the standard normal distribution to do things like we did in the case of confidence intervals. But in the case where you don't know, either you don't have a big enough sample size or you don't know that the underlying distribution is normal, you're going to have to resort to using the t-distribution, just like we did in the confidence interval case. And that ought to tip you off to the fact that we really are just doing confidence interval analysis here. We're just seeing it in a different context. Rejection region is, okay, once I do a computation with my test statistic under the assumption of the null hypothesis, how outlandish can I be with my test statistic before I'm willing to say that was kind of a dumb assumption? Okay, and that's what the rejection region is. You figure out, okay, if it's this far outlandish, I'm going to reject. Okay, that's the rejection region. And the probability that you're willing to make a mistake in doing that rejection is what you call alpha. It's called your alpha level, and that's the type 1 error. Okay, that's where you make the mistake of rejecting the null when in fact it is true. Okay, but the type 1 error is the far less egregious error, so that's the one we want to control. Remember, the other one is not rejecting the null when in fact it was false. Okay. So you compute the necessary sample quantities and substitute into the test statistic, okay? And then you decide whether to reject or not reject the null, okay? All right, so let's do this. Well, last time we kind of looked at this quickly. So the first case that we're going to consider is kind of like the first case we did in the confidence interval situation. Namely, we're going to assume that we know the underlying distribution is normal and we have a known standard deviation. Now, this might seem like a bridge too far, like that it wouldn't happen very often. And that might be true, but there are situations you run into where you know the underlying distribution is normal. You know the standard deviation for the population, but you've changed some testing protocol. Maybe you changed the SAT test slightly. You know that the spread of the data is going to be roughly the same. You know it was normal from before. And so now you're interested to know how did it shift? Because certainly the mean shifted, okay? So in that case, you kind of know, what the population distribution is. It's normal. You know the population standard deviation, but you don't know the mean anymore. Maybe the mean went up or down, okay? So this case is not all that, ridiculous to think about. It does happen, okay? So X has a normal distribution. We know sigma. This means that if H0 is true, okay, remember H0, just to remind you, okay, so what was the deal with H0? Remember H0, we're only doing tests about one mean, so it's just that the population mean is equal to some specific number, U0, okay? And then the alternative hypothesis is one of three things. It's either mu is different from mu0, mu is greater than mu0, or mu is less than mu0. You're gonna have one of those situations that you're considering. These two situations right here are one-tailed tests. Okay, they're almost like one-sided confidence interval situations. And this one right here is a two-tailed test. Okay, you're going to be willing to reject the null if you get too outlandish in either direction. Okay. All right. So if the value, so first of all, you take X bar, your sample mean, you subtract the mean that you're assuming the population mean is, and you're dividing by the sample or by the standard deviation of X bar, which is just the original standard deviation sigma divided by the square root of n. We've seen why that's true before. And under this assumption, that thing's going to be standard normal because the standard deviation of X bar is just sigma over the square root of n. Okay, so that's going to be standard normal. If the value of that thing is really large or really small in the standard normal table, then you know that X bar is far away from the mean, okay? Which means you're in a really unlikely situation. Okay, this suggests that the assumption that mu is equal to mu0 is incorrect. So you would tend to reject the null. Now there's some caveats here, like for instance, if my alternative is that the true mean is bigger than mu0, okay, and I ended up with a test statistic that was far below mu0, like X bar minus mu0 is like hugely negative, then I'm not going to tend to reject the null in favor of that alternative hypothesis. Okay, so we'll see that before long here, though. Okay, all right. So let's look at this. Okay, so here's our test procedure. Assuming mu is equal to mu0, our test statistic is z equal to that thing. Okay, and then here are our three alternative hypothesis situations. Okay, so I mean, essentially what's going on here is you're assuming that mu0 is the mean. Okay, so this is the general situation that you're in. And of course, if you create, right, if you take z and you set it equal to X bar minus mu0 over sigma divided by the square root of n, then this is going to become the standard normal distribution where you have 0 in the middle and a standard deviation of 1, right? So this is the standard normal distribution over here, okay? So this is the original distribution over on the left, and if we convert to the z score, we're going to be in the standard normal distribution instead, okay? So when would so if I was like in the first situation right here, mu greater than mu0, okay? So mu greater than mu0, if mu really was greater than mu0, okay? Maybe mu was like up here or something like that. So if mu was up here, okay, so, if mu was up here, then I know that the true bell shape is probably more like this, okay? It's probably more like this. So if I end up with a test statistic like X bar that's like way up here somewhere, okay, so if like X bar was way up here, like hugely positive, then I'm starting to think that mu really is bigger than mu zero, that the bell shape really should be shifted to the left, okay? So that's why I kind of pay attention to the right tail in this particular case. So this right here is often referred to as a one-tail test, but it's also referred to as a right tail. This is a right tail test because the rejection region is going to be to the right, okay? So in this case, you know, I locate this number z sub alpha, right? There's alpha right here. And if I end up with a test statistic that is way up here in this region above z sub alpha, I'm going to reject, okay? And so that's this situation right here, okay? What's it going to look like in this other situation? Well, if mu is less than mu zero, then you would expect to fall into the left tail, and that's where you're going to tend to reject, right? The X bar would tend to be to the left of mu zero. If the true mean was below mu zero, right, you would expect to be on the left side, okay? So the rejection region in this case is going to be like this, okay? So you're going to have this minus z alpha thing down here. Right, again, all of it is down here because after all, I'm not going to reject in favor of this alternative hypothesis, mu less than mu zero, if I end up with a test statistic that's to the right of mu zero. That's not what I'm interested in doing here. Like, I would only start to believe the alternative hypothesis in this case if I end up with a test statistic that's way over to the left of mu zero. Then it's like, well, maybe the normal bubble is actually lower than I thought, okay? So again, the alternative hypothesis in the first case, the right tail case, you know, I'm only going to reject if I end up with a big test statistic. I start to think, oh, maybe the bubble shifted to the right, okay? In the second case, I'm thinking, oh, if I end up with the test statistic far to the left, I'm going to say, oh, I think that the bubble's actually shifted to the left in this case. So this is called a right tail or a left tail test, sorry. Left tail test, okay? And then again, this guy right here, this is a two-tail test. Two-tail test, okay? So what's the rejection region going to look like here? Well, it's going to look like this over once we convert to the standard normal. In this case, I am going to actually reject if I'm either too high or too low, right? And I want to split alpha between the two sides, right? So how much does that mean there's going to be over here? Well, alpha over 2 and alpha over 2. So this number here is z alpha over 2, and this guy is negative z alpha over 2. Okay, by definition, those z sub whatevers are just the numbers that have that percentage above it. Okay, we've seen that before. Okay, so again, we have a right tail, right? I'm only going to reject in favor of the alternative if I end up with something that's too big and makes me think that the true distribution should be shifted to the right. Okay. Mu less than mu zero, I'm only going to reject if I get a really far left test statistic, which makes me think the bubble should be shifted leftward. And mu different from mu zero, well, there it's like if I'm too big or too small, I start to suspect that the mean is something other than the one that I have, or that I assumed at the beginning under the null. Okay. All right. So here's just kind of a pictorial rendering of what's happening here. Okay. So I'm under the assumption that H0 is true, right? Remember that H0 is just the assumption that mu is equal to mu zero. Okay. I go over, right? I subtract mu zero, divide by the standard deviation, sigma over the square root of n from x bar. And then you are in the standard normal distribution. And this right here is a situation that corresponds to aha, right? Alternative hypothesis of mu greater than mu zero. This guy corresponds to a ha that is mu less than mu zero. And this guy corresponds to a ha that's mu different from mu zero, okay? Yeah, so there's the picture right there, okay? I kind of had already drawn that on the other slide. Okay, so let's look at an example here. The melting point of each of 16 samples. So let me just kind of write down what we know so far. Okay, so N is equal to 16, okay? Of a certain brand of hydrogenated vegetable oil was determined, resulting in an sample average, sample mean of 94.32. Okay. Assume that the distribution of the melting point is normal with sigma equal to what? 1.2. Okay, so what does that mean sigma of x bar is? Well, that's going to be sigma over the square root of n, which is going to be 1.2 divided by 4, which is 0.3. I don't even need a calculator for that. Yeah. Okay. Assume that the distribution, okay, right. So let's test these hypotheses. So I have a HO or a null hypothesis that mu is equal to 95. So this 95 right here, that's my mu zero, right? The thing that I've been talking about. And the alternative hypothesis is that mu is different from that. That mu is actually different from that using a two-tailed level, alpha level. So this is our alpha right here, right? So this is alpha. So I have alpha equal to 0.01. Okay, well, because of the form of the alternative hypothesis, I know I'm going to have a two-tailed rejection region. Two-tailed rejection region, okay? And what is, so let's see here. I know that alpha over 2, since it's two-tail, right? I need alpha over 2, and alpha over 2 is 0.005, okay? 0.005. So I know I'm going to have a rejection region like this, okay? So this is z sub 0.005, okay? That means that up here is 0.005. And of course, by symmetry, that means that negative z sub 0.005 has that same percentage down here. Okay, so what are these z's? I really just need z sub 0.005. What does that equal? What is that going to equal? Well, let's have a look here. Okay, I'm just going to go in our table over here. Standard normal table. I'm going to leave the writing up here for now because I want to still access that. So actually, I can get it out of the student t distribution also, because at the bottom are all the z values. The z values are all right down here. Okay. And let's see here. What do I want? Well, 0.005, that's like 0.5%. Right, so that's, you see this right here, it says 99.5% is on the left of this, okay, is to the left of this particular value. That means 99%, if I were to reflect it over and put the same percentage in the two tails, I'm at 99% in the middle. And that's the same thing that I want, right? 99.5 to the left. If I were to reflect this over, I would have 0.5 percentage point in each tail, which would be 99% in between those two things. So what's the z value that corresponds to? Well, it's right here. It's 2.576, basically, 2.576. Let's write that down. 2.576. 2.576. All right, let's go back over here and get back into the proper view here. Here we go. C sub alpha over 2 is 2.576. Okay, so what's the test statistic here? So that means that we're going to reject, by the way, you reject the null if the test statistic, which is z equal to x bar minus mu 0 over sigma divided by square root of n, is greater than or equal to 2.576 or less than or equal to negative 2.576. Okay. Well, what is this thing? Let's see. So the test statistic I get is that z is equal to 94.32 minus 95 over what? Sigma over the square root of n. I already computed that. That was 0.3. Okay, so what do we get here? 94.32 minus 95. 94.32 minus 95. I think that's about negative 0.68. Over 0.3. Okay, which is, let's see here, get my calculator. Okay. Negative 0.68 divided by 0.3. I get negative 2.267. Okay. Negative 2.267. So what's the conclusion? You don't reject the null. So you don't. Right? That's not low enough. Don't reject the null. Okay, so that's kind of the conclusion that we come to in this particular case. It's not small enough. Okay, not small enough. Okay, we get negative 2.267, which is not smaller than negative 2.576. Okay. So what is the connection, by the way? And I said I wanted to show you what the connection was to a confidence interval. And indeed, let's kind of take a look at that right now. Okay, so what's the connection to a confidence interval? Well, let me sort of clear this out, and we'll think about this together carefully right now. Okay, so here I had a 0.01 test, right? So look, what if what if I made a 99% confidence interval? 99% confidence interval for the mean mu, okay, which is kind of unknown to us. Well, you know that that's going to be x bar plus or minus. In this particular case, it's going to be z sub alpha over 2 was z sub 0.005. Now remember, we already figured out what z sub 0.005 was. That was 2.576. Okay. Z sub 0.005 times sigma over the square root of n. Okay. So what is that? Well, that x bar, okay, so this is equal to, what's x bar? 94.32 plus or minus 2.576. Now remember, we already computed sigma over the square root of n before. That was equal to 0.3. Right, that was 1.2 divided by 4. Okay, so what does that end up giving us for the confidence interval? Well, it's going to be 94.32 minus that thing. Okay, so let me just kind of do that. 94.32 minus 2.576 times 0.3. 93.5472. 93.5472 is what I get on the one side. and then 94.32 plus 2.576 times 0.3 is 95.0928. 95.0928. And now, so that's a 99% confidence interval for the population mean. Now let me ask you, does mu equal to 95 belong to that interval? Is it in there? Yes, it is. So that means I do not reject, right? So since 95 is in here, we do not reject. Right, so we see a clear connection to the confidence interval situation. And in fact, that's how we actually build the hypothesis test concept on the back of confidence intervals. Okay, these are 100% correlated to one another. Okay, so that's very interesting. Okay, so it's all connected. Okay, so let's move on here. Next one. So in the next case, this is going to be similar to what we did for confidence intervals. Now we're going to say, well, maybe I don't know that the underlying distribution is normal necessarily. Okay, but I know that the sample size is quite large. I think before I said bigger than 30. It turns out that in hypothesis testing, you want to be a little bit more careful. So you say 40, you know, is kind of the baseline time when you're willing to invoke this particular case. That's what large sample is going to mean to us here, okay? Of course, if you know that the underlying distribution was already, it looked kind of bell-shaped just based on making a histogram or something, then 30 is probably fine, to be honest with you, okay? And you don't know sigma, okay? You don't know sigma. So large sample size, don't know sigma, just like in the confidence interval situation. If H0 is true, then you can actually invoke the central limit theorem. You have an approximately standard normal distribution, even though you're using S, the sample standard deviation, in the place of sigma, okay? Test statistic, again, oops, that's a typo. This should not be sigma since I don't know it. What should be here? It should be S, the sample standard deviation, okay? Sample standard deviation should be down there. All right, so again, same kind of setup. The only difference is you don't know the standard deviation of the population. All you know is the one from the sample that you just took, okay? All right, so that's the setup. And the third case is N is not necessarily large. And in fact, it might be small, might be like 5 or 6. X is normally distributed, and we do not know sigma. And actually that normally distributed thing, that's not exactly necessary. Okay? You should just say, symmetrical or something. Symmetrically. Right, normally distributed isn't necessarily an assumption you have to make here. You're being very conservative because you're going to invoke the t distribution with n-1 degrees of freedom. Okay, you can't use the central limit theorem because n is too small. If H0 is true, then that t equal to x bar minus mu 0 over s sub x bar, which is just s sub x bar is just s over the square root of n, as a t distribution within -1 degrees of freedom. So there, instead of looking stuff up in the z table, you're going to look it up in the t table. Okay, look up the specific t distribution within -1 degrees of freedom, and that will do the job for us. Okay. Right, similar situation here. But the rejection region is set up differently. So for case 2, where you had a large sample size, okay, So let's see here. Case 2, large samples, not necessarily normally distributed, okay? But large sample size, and you're using S. Here, you don't necessarily have to have normally distributed, but the sample size isn't necessarily large. You don't know sigma. You're going to use the t distribution. So the setup for this one is exactly the same as it was for this first case back here. Okay, so same kind of situation, same test statistic, except sigma is getting replaced by S. And same, and of course you replace sigma with S in the formula for the confidence interval also, if you want to think about it that way. But you still use the Z distribution in this case. For this other one though, you have to use the T distribution to figure out the cutoffs. Again, you're going to tend to reject in favor of the alternative. In the case where mu is bigger than mu0 as your alternative, if you have a test statistic, a t test statistic that is bigger than or equal to some value. So you would look up t alpha n minus 1. You would put all of the alpha in the one tail, in the right tail. Okay, again, so this is all of the alpha is in the right tail. This one is saying all of the alpha is in the left tail. And in this case right here, you're splitting the alpha between two tails, just like you did before for the Z. Okay, but you have to use the table slightly differently, of course, than you did for the Z. Okay, that table I was using in Wikipedia is sort of convenient because you kind of have the major Z values at the bottom, and you can get any of your T values there as well. And of course, you could always figure this out in Excel also, but why? Why? If you have the table right there, you can just look it right up. Okay. A certain sample of size 26 has a mean value of 370.69 and a standard deviation of 24.36. Okay. So this is a sample mean. Okay, so n is 26. Okay, what's true? So x bar is 370.69. Okay, the sample standard deviation, S, is equal to what? 24.36. Okay. Suppose the investigators believed ahead of time that the true mean in the population would be at most 6. Would be at most 6. Okay. Does the data contradict this a priori belief? Okay, so how would we set up the null and alternative hypothesis? Well, what you do is you say, okay, what is the worst thing I would be willing to accept here? Well, so they believe that it's at most 6. So the worst would be if it was actually 6. So mu equal to 6. Okay. And when would you tend to reject this at most 6 thing? Well, if it was clearly bigger than 6. Okay, so the alternative hypothesis is that mu is bigger than 6. Does the data contradict this a priori belief? Okay, does the data predict this a priori belief? Well, I mean, here's the thing. You kind of have a big standard deviation here, okay? But, I mean, seriously, I have an at most 6 thing going on here, okay? And I got a sample mean of 370.69, which seems like it's hugely above 6, okay? So we start to suspect that maybe, yeah, we're going to clearly reject this thing. So first of all, I could do by the way, which distribution am I going to use here? Well, I'm going to use the t distribution. And here they want the significance level to be 0.05. So that means I'm going to use alpha equal to 0.05. And it's going to be which kind of a test? Well, I'm only going to reject in favor of the alternative if mu, right? If I end up with a test statistic that's too big. So this is a right tail test. A right tail test, okay? And what's the distribution that I'm going to use here? So like, here's the thing. I'm going to use the t distribution. Which t distribution am I going to use, right? They all have 0 as their mean in the middle. Well, it's going to be t sub 25 because, right, degrees of freedom, right, which is nu, right? So that's the degrees of freedom is equal to n minus 1, which is 25, right? N is 26, so n minus 1 is 25. Okay, so here I'm going to put all the alpha, and I'm only going to reject if I'm too big. So I'm going to reject if I get up here too far. And this is going to be t sub what? What's alpha? Well, 0.05. It's all in one tail, comma, 25. Right, so how much percentage is below this thing? Well, 95%, right? So there's 5% above this thing. Okay, so 95% below it. I'm going to leave this writing on here as I go over into the table on the other side. Okay, so we'll figure out what this t sub 0.05, 25 thing is. Okay, so let's see here. I want 25 degrees of freedom. I see that there, but I want 95% below it. Okay, so 95% below it is right here. Okay, so I'm going to be in this column right here. I'm going down, and where's 25? It's right here. Okay, 25 right here. So 1.708. Okay, so this guy right here is 1.708. Okay. Yes. Back over here. So the rejection value is 1.708. Well, what's our test statistic? Okay, so test stat is what? Well, it's going to be t equal to x bar minus, now remember, we always start by assuming the null, which is that mu is equal to 6 divided by s divided by the square root of n. Okay, so s over the square root of n. Okay, and I'll compute that real quick. So let's see, it's going to be x bar. X bar is a ridiculous thing. It's 370.69 minus 6. Okay, and then I'm going to divide that by s over the square root of n. So it's going to be 24.36 divided by the square root of 26. And I get 70. I get 76.34. And that is way bigger, right? So that's way bigger. Well, that's way bigger than our cutoff. Okay, so that's bigger than t sub 0.05, comma 25. So what do? We reject the null. And of course, the confidence interval situation here, I would do a 95% confidence interval. Okay, so that would be x bar plus or minus. I would use the t again, x bar plus or minus. Well, actually, no. I wouldn't do plus or minus in this case. Okay, because in this particular case, all I want to do is, this is going to be a one-sided confidence interval. Okay, this is going to be a one-sided confidence interval. And when am I going to reject? Well, I'm going to tend to reject it if I'm going to tend to reject this thing if I get too big, yes? Okay. So, so how would I do this? Well, actually, what you do here is you go x bar minus, you go x bar minus t sub 0.05, comma 25, okay, times s over the square root of n. Okay, so what does that equal to? And by the way, that's going to be your left end, and then you're going to go up to infinity. Okay, and if you belong to this thing right here, if you belong to this thing right here, then you feel pretty safe. Okay, you belong to this thing right here, you feel pretty safe. But if not, you're going to tend to think that something is wildly wrong. Okay, so let's go ahead and compute this thing. What does this end up being? Well, x bar, which is 370.69. I subtract the t value. Okay, what's the t value? 1.708. 1.708 times what? Times s, which is 24.36, divided by the square root of n, which is the square root of 26. And I get 362.53. Okay, so the left end is 362.53, infinity. And you say to yourself, huh, okay, so that's like a 95% confidence interval for the mean mu. Okay, so which of these two, between the alternative and the null hypothesis, which of these two seems to be the one that's more compatible with that? Mu equals 6? No, not mu equal to 6. 6 does not belong to that interval, clearly. Or mu greater than 6. Well, mu greater than 6. Therefore, you're going to lean toward the alternative hypothesis in this case. Okay? So you can think about it as a confidence interval situation if you want, right? Just to kind of help reinforce the confidence interval paradigm. You could also just compute the rejection region and reject based on the test statistic being, too outlandish relative to that cutoff point and being in the rejection region also. Okay? Yeah. All right. I think I'm going to stop right there for now because the rest of this has to do with converting everything over to a different way of thinking about things. What we've done so far is we've tested hypotheses and we've rejected or not rejected based on some cutoffs and thinking about critical regions. But it turns out in a lot of medical journals and things like that, they do this thing called computation of a p-value, which isn't that different from what we were doing, but it's just slightly different that it's going to take a little bit of development. So I'm going to wait until the next lecture to do that. But you should have all the tools you need at this point to complete the exam. No question about it. This stuff is just really kind of for your benefit. Just stay tuned. Monday, I'll talk about this a little bit. It would be helpful and for your own future endeavors as it pertains to like reading papers, articles, things like that, to know what the p-value concept is. But I don't actually draw that out in the final or anything. But I would encourage you to go watch the lecture nonetheless. It'll be short. We'll develop it, and that will be the end. Okay. Hopefully you come check that out. Hopefully you've enjoyed this course. We've done a lot of stuff. Believe it or not, I got through everything that I wanted to get through, which is sort of miraculous in some ways. Got all the way to hypothesis testing and statistics, which I didn't think was going to be possible at some point, but then we did it. So I'm grateful for that. Hopefully you feel like you've learned some stuff that will benefit you later on. I've enjoyed teaching it, enjoyed spending time with you guys and getting to know you. Sorry things ended up not being in a face-to-face format. We had to go to this paradigm, but hopefully it wasn't too jarring and you enjoyed it, even in this venue. Okay? It was great teaching you guys. Please go fill out the course evaluations. That's always a helpful thing for me to get feedback on certain things, especially after having to shift over to this other venue. I counted it a privilege to teach you, but again, I'm sorry that things didn't work out in a more standard, normal way. All right, I will see you later.